Okay, so this is Generalized Linear Models with examples in R, Chapter 4, and one question 4.6. And 4.6 piggybacks off of 4.5, so you can use 4.5 as reference for a lot of the little sub-questions here. Okay, so we'll just march through this bit by bit. So first we need to generate some random data, and we'll call that y. That comes from an exponential distribution, so I'm going to use the rexp function here, and I need n 100 samples, and this distribution in R is parameterized not with mean but with rate. Okay, and rate is defined as 1 over mu, where mu is the average value. Okay, so there you go. So in other words, I could just make this 1 because it's 1 divided by 1, but I did this just to be explicit. And then I have an estimate for mu, which is mu hat, which is just the mean of my distribution. Okay, so we have all of that. And what we're doing in part 1 is we're going to plot the likelihood function, and I'll also plot the log likelihood function from a range of values, possible values for mu here. Okay. So we already have the likelihood function and the log likelihood function from question 4.5, and so we're going to plot that. So I have mu seek. Okay, so this is just the candidate values that we're going to plot. And then I'm going to get my likelihood and my log likelihood by first getting the likelihood, making an empty vector for values of the likelihood. So I'll get 1,000 different, oops, didn't mean to do that. So I'll get 1,000 values for my likelihood and 1,000 values for my log likelihood. But right now there's just these empty vectors. And to fill them up, I run this for loop. And you can look at the for loop to kind of figure out how it's working. But we can run that. And I just plug in the expressions in kind of R version for the likelihood and the log likelihood. Right? So we have that. And now we're going to plot this. I'm going to plot this in a few ways here. Okay, so the first thing I'm going to do is I'm going to plot the likelihood function in black. Okay, so you see it in black here. It's interspersed because it's being cut by the log likelihood. Okay, so we'll get to that in a second. But the log likelihood, I'm going to plot that, but I'm going to exponentiate it, right? So I'm going to reverse the effect of logging, the function. Okay, and you see that they're the identical function, which is exactly what you would expect. Okay. Now I'm also putting in some vertical lines at our value for mu hat, okay, which was 1. Actually, it wasn't. It was our estimate for. It was the average of our value of our data, and I'm also plotting it at the max or at the peak of our curve here. Okay, and you notice that they completely, and so one is in black and one is in blue, but you notice that they completely line up right at the peak there, right, because mu hat is the place at which our likelihood and log likelihood peak. Okay, and then I've also plotted the null hypothesis of mu equals 1 in red there. Okay, now I'm also going to plot just the log likelihood function, not exponentiating it, and that's right here. Okay, and it looks like this. But again, notice a few things. Notice that so I've plotted the peak value once again, okay, of the function and also mu hat, and notice that they align once again, and that they align at the exact same place where the likelihood function aligns. Okay, and this helps justify using the log likelihood rather than the likelihood, because we get the same, we get the same mu that produces the max likelihood or log likelihood. Okay, and it just so happens that the log likelihoods are just easier to work with. Okay, so hopefully that makes sense. Okay, so now in part 2 we're going to test the hypothesis that mu equals 1 using the Wald, the score, the likelihood ratio statistics, and we found all of these for our distribution in the previous question, so they're all right there. So all I'm going to do, so I have some extra code up here for the log likelihood and stuff like that that we'll use later. So you might want to refer back to that as you encountered in the code. But so here's my my Wald statistic, my score statistic, my log likelihood ratio statistic, and to find the p-values, which is more or less what we're being asked to do here, we use the p-exp function and fill out the appropriate, fill out appropriate arguments for the function. And I'm rounding it just to keep it from looking overwhelming. Okay, and you notice that we get the same p-value for each of these. All right. So now we're going to plot the Wald score and likelihood ratio statistics, and we're going to we're going to do that. And it says to use a horizontal line to show the location of the critical value for chi-squared. But the way that I'm going to plot this, it doesn't really make sense to do that. You know, the answer in the back of the book gives a different impression of what it wants you to do. So, you know, if you want to be able to plot this in accord with the question, then look at the back of the book. What I am going to do is I'm going to plot the log likelihood function, but I'm going to zoom in just to this top region right here, okay? And I'm going to show where the Wald statistic and the score statistic and the log likelihood ratio statistic kind of lay there, okay? So again, here the black line is mu hat, and then the red line is the null hypothesis of mu, okay? And we can visualize the Wald statistic as just the horizontal distance between the two estimates. Okay, so that'd be one way we could test a hypothesis. If W was big enough, what is big enough? Well, it'd be a critical value of chi-square here, which happens to be 3.84. If that was big enough, then we would reject the null hypothesis. Okay. Now, another thing that we could do is we could look at the slope of the log likelihood function at mu hat, or I'm sorry, at the null hypothesis for mu, right? Now the idea is that at the peak of a curve, the derivative is 0, right? It's just a horizontal line across here. But if I were to, if I key in on the null hypothesis, if the null hypothesis was really far away, right? So let's say that we had that the null hypothesis was way out here at maybe 1.2. Well, you would see a very large magnitude of derivative, and that would suggest then that the null hypothesis is falling far away from the estimated value of the parameter. Okay, and so that's what we're doing here. Okay, so this dotted line here is the derivative of the log likelihood function at the null hypothesis, and you can kind of see how I've constructed that here. It's basically taking the derivative of the log likelihood. So you'll have to do that by yourself. I didn't show how to do that, but you take the derivative of the log likelihood at mu. Okay, and again, there's a critical value for this, but we're not plotting it. And then finally, the log likelihood ratio statistic. So I think that the best way to look at this is the difference in vertical height from mu hat versus mu here, okay? And so I've represented that with this gray line going across, and so it would be the distance, the distance from mu up to mu hat. Okay, so that's how I've done all of that. Okay, so now we need to find the standard error here. So we've already found the analytical expression for it in question 4.5, and so here we can just put that into our into R, and we get a standard error of this. Okay, and then we can get a confidence interval, and you can see how I've done the confidence interval. It's just it's mu hat minus the standard error times an alpha value here. That corresponds to what is that? 3 standard deviations or 2 standard deviations. Can't remember what 1.96 means, but it's easy enough to find. And so then we get our confidence interval, 95% confidence interval. Okay. Yeah, it must be. If we're looking for 95% confidence interval, then it's two standard errors. Okay, well, I'll call that good.